Thank you, Hernan. My name is Dan Miller, as Hernan already stated. I'm a manufacturer's rep for Hazard Control Technologies. I'm also an encapsulator specialist. My background includes 40 years in the fire service in municipal class cities and small communities as well. I was a battalion chief with the Omaha, Nebraska Fire Department for many years. I retired from there and became a fire chief in a community of about 25,000 in Nebraska for 4 years. But for over 38 years, I was also a volunteer firefighter in a small town in Nebraska. But I do also have 30 plus years of experience in the electronics field and field service and repair and electronics, as well as I do some teaching for hazard control technologies for our clients in coal handling hazards awareness and emergency response to incidents involving coal in power plants and refineries and so forth. Our focus today is going to be on power generating facilities, fire hazards awareness. So we're going to talk about the different hazards and being aware of those hazards and all of the different parts of the generating side of the power grid. We're going to talk some about encapsulator technology as well and how it can answer some of those hazards. And we're going to look a little bit at how we can better detect, correct, and prevent problems from occurring. And then we're going to look at some specific hazards, for example, coal dust, explosions, large power transformers, etc. And then towards the end, we're going to talk about the different resources that not only that HCT has available, but our services that we have available, training, engineering, and other resources as well. I would like to ask you to put any questions that you have in the chat. That way, as you think of those questions, if you put them in the chat later on, we're going to have a question and answer period, and we can answer those questions in the order that they were received, and then we won't forget about them either, which is pretty important. Initially, I would like you to all put in the chat your name and where you are from, what company you represent. That would be excellent. That way we have a pretty good idea of where everybody's from and get a little better overview amongst the participants who are participating today and get to know each other a little bit. So our objectives today are going to be to understand common power generating facility fire hazards, to be able to describe various explosion, fire, and vapor hazards that occur in and around power plants, to understand encapsulator technology and how it can interface with the fuels and the hazard types that are common to the power industry, and then, of course, to answer any questions that you may have. So when we look at the different types of steam and electric power plants, there's a range of them, and that range is growing every day, it seems like. So we look at biomass plants first. Over on the left, biomass involves wood and natural products. And then, of course, we have coal, which has been around for a long, long time. Some of those plants are being sundowned and phased out, but other ones, they're finding out, well, to maintain extra energy on the grid and resilience to natural disasters, as well as to keep up with the demand, say in electric vehicles, they're needing to keep those going for a while longer. And I know in some of your countries, they've just fired up new coal power plants and or restarted some old ones. We also have refuge gas power plants that energy comes as a gas out of landfills. Landfills generate methane, and that's used to either fire up generators or develop steam to spin generators. And then we have natural gas itself. For example, here in Nebraska, the U.S., the public power plant just put in 9 new natural gas engines to spin turbines and develop more electricity. I think something like 15 megawatts of energy is going to come off of that. And they installed 9 of these natural gas engines, each weighing in at about 900,000 pounds. Nuclear power, a very clean source of energy, kind of gets a bad rap here and there, or bad reputation, but it's a very clean form of energy. And I know, although here in the U.S. it's hard to fire up a new nuclear power plant, it seems. Other countries are doing it, which is great. Solar fields, individual solar panels on homes, etc. They're really becoming more predominant. And then, of course, also in the renewables area is wind power. Wind power here in the Midwest part of the U.S. is growing all the time, as well as the solar fields. More and more of the wind turbines going up everywhere. And then we have the hydropower, the power dams on different rivers and tributaries that are and have been in service for many, many years. I heard an interesting hearing going on earlier today online, where it seems that now hydroelectric power is being used for peak energy, whereas the combination of solar and wind and some coal are being combined for the base load. The hydroelectric dams are predominantly being used for peak energy. They can turn them on and off, and or throttle up or down their electric generating capacity based on the number of turbines they have, and based upon need and who's purchasing it. So those are all the different common types of electric power plants and generating plants. Something new that's come along as a feature of the grid, however, is lithium-ion energy storage systems, or battery energy storage systems. Sometimes we call them BESS for short. They're a feature of the grid that helps us store energy that we develop when conditions are favorable. And then it is used to stabilize the grid and or for peak shaving and so forth as needed. And those present a hazard of their own, which we'll discuss as well. So if we look at the incidents that are most likely to happen in the power generating industry, fire and explosion are the 2 biggest ones that tend to create the most damage to infrastructure, as well as harm employees and really cause a big hazard. And as you look down the line, you look at mechanical failure, collapse of the infrastructure, electrical grid failure, natural hazards like natural disasters, and then human errors weigh into that as well. And we'll talk about human errors and how they relate to all of the rest of the modes of failure as well. So common significant hazards that occur in the industry or industry-wide, of course, high voltage, always a big hazard. We try to tame it as much as we can, but if we have any kind of a failure due to high wind, tornadoes, hurricanes, ice, etc., it can cause damage to the infrastructure itself, and then that high voltage comes into contact with people and objects. And for example, in California, I know high voltage power lines have been blamed for many of the forest fires and wildland fires that have occurred in California over the last few years. High temperatures, we're dealing with boilers and steam and so forth. Those high temperatures are a different type of hazard within the power industry that always need to be managed appropriately and sometimes need to be mitigated as they get out of control. High pressures, dealing with steam, hydraulics, different types of gases for cooling, etc. Dealing with a lot of high pressures, high speed rotation of the machinery and the generators themselves, spinning at high speeds, create a lot of momentum and friction and so forth. They are a hazard in themselves as well. And then the many different kinds of fuels involved in the power industry. So we have solid fuels in the form of coal and so forth, liquids, combustible metals, combustible dusts, and those dusts can accumulate and actually begin to combust while they're in a silo, for example, as the coal degrades or gets wet or gets too dry, and also in piles and so forth. And that combustible dust can then turn into a combustible dust explosion if we don't mitigate it or manage it correctly. And then one thing we touched on before is unfamiliarity. So what's happening, especially in the coal industry right now, is as they sundown some of these plants, many of the old employees that used to know how the facility operated, or maybe even were there when the facility was built and know all the peculiarities of that particular facility, those people are gone or retired or maybe even deceased because of the age of the facility. Well, a lot of new people that come into the facility are really unfamiliar with the time-tested procedures and safety features of that facility, and those kind of things can get missed or underappreciated, and that results in hazards occurring and growing because of human error. Many of the power plants that are being sundowned are being run by private contractors who aren't that familiar with the facility and how it came to be, and all the modifications that were made over the time, all the engineering changes that occurred, and things like emergency planning and so forth. They're just not as familiar as employees that have been around for a long time. So that's always an ongoing challenge of keeping people trained and aware of the hazards that they're dealing with, as well as the specific facility features and plans that are needed to carry out a safe process. There's a lot of factors that go into running a steam and electric generating facility, and we're gonna hit on a lot of those today, like dust collectors and substations and storage bins and barns and oil igniters and boilers. There's just a lot of things going on, a lot of moving parts to generating electricity. And then there's the process itself and the human interaction that goes into it. And then there's the accident prevention that needs to take place, as well as safety features and systems that are put in place to keep those problems under control. We're going to try and hit on most of those things today. So there's several different fire classes and extinguishing agents that we all need to be aware of, and need to be aware of the limitations of many of those agents as well. So Class A fires involve wood, paper, coal, some of the different fuels that are going into there. There was even one that we ran into recently that they're using recyclables, recycled plastic bags and paper products, and then they're making those into pellets, and they're blending that in with the coal mix as they fire their boiler. Those are Class A materials. Class B materials are your liquid ignitables and gaseous ignitables. So any ignitable liquid or gas is a Class B. Class C is energized electrical circuits. So as you can imagine, the biggest hazard there is becoming energized yourself, which we try to de-energize the circuit before we make any kind of a fire extinguishment attempt, but that's not always possible. And then Class D is combustible metals, things like magnesium, shavings, titanium, etc. And then we have the new classification, anyway, of fire that's not really an official class yet of its own, but they are working on a classification for lithium-ion batteries to be in their own class. So as far as the extinguishing agents go, if you can look at Class A, water works pretty good, although it has some limitations with high surface tension and a non-uniform absorption of heat. Carbon dioxide is a gas that its primary feature is to exclude oxygen from a confined area so that a fire is extinguished that way by the exclusion of oxygen. Dry chemical fire extinguishers interfere with the chemical chain reaction and knock down the flaming of the fire. And dry chemical extinguishers, the ABC dry chemical extinguishers are obviously, most people are very familiar with those. One of the limitations of those is that they don't cool well in objects that have deep-seated heat. And another limitation is just the fact that most dry chemical extinguishers only last about 30 seconds and they run out of dry chemical. Then you have dry powder extinguishers that are specifically for Class D or metals fire. They try to encrust that metals fire and starve it of oxygen until it has time to cool down. And then foam as an extinguishing agent is mostly a mechanical feature of fire protection that is trying to create a blanket of bubbles on top of a liquid fuel that is static and not moving. And it has to be static and not moving for that foam blanket to stay intact. If the fuel is moving or spraying, then you have to use a dual agent or a different agent that we'll discuss in a moment. And then we come to the wetting agents. Wetting agents are a product that specifically breaks down the surface tension of water and helps it soak into Class A materials better. So the agent we're going to talk about a little bit later on in our presentation, and the one that Hazard Control Technologies has manufactured for many years, is called F500 encapsulator agent, or encapsulator technology as far as the classification goes. But F500 it's a water additive agent, and we're going to show you shortly how it interacts with fuels to make it applicable to all the different classes of fire. So we're going to talk a little bit about encapsulator technology here and the chemistry of fire. So to create a fire, you obviously have to have some fuel, heat, and the presence of oxygen. And then you have to have all of those three come together in a chemical chain reaction. When that chemical chain reaction occurs here on Earth's surface, we always have incomplete combustion. So that incomplete combustion creates something called free radicals. Free radicals are atoms with an imbalance in their electrons, and they're always seeking to mate up with other free radicals. And in that process, they create a myriad of compounds in the atmosphere that are both flammable and toxic. Things like carbon monoxide, hydrogen cyanide, hydrogen fluoride, but all those elements come together as they're seeking to coalesce back together and form those new compounds. And those new compounds are explosive. They help advance the fire and make it grow as they spread. And they also form the toxic compounds that can cause any of us cancer and or immediate acute respiratory distress and death. So the free radicals are a very have a negative impact on humans and the environment and the fire growth. So encapsulator agents came about in about 1996. Hazard Control Technologies, as it is currently known, acquired the patent rights to a water additive agent that has superior cooling properties. It's effective on Class A, B, D lithium-ion battery fires, as well as pressurized and what we call three-dimensional fires that involve moving liquids, spraying liquids, and cascading liquids, and hydrocarbon-based fuels and polar solvents, including ethanol. And it's even applicable on Class C fires if we're the least bit careful in how we apply it, and we apply it with a broken stream, which is part of the training that we provide. The encapsulator agent, it's marketed under the name of F500 EA, or encapsulator agent. And it's we term it as the technology for the third millennium and all the modern fuels and threats that are seem to be prevalent today as technology moves forward. So we recognize the need for an environmentally responsible extinguishing agent that's highly available and is a good, responsible choice for people to choose as an alternative to things like dry powder, foam, and wetting agents. And F500 is UL classified for Class A and B fires in the US and Canada. It was UL classified many years ago as a wetting agent, and we're currently working on it as getting it classified under a new standard called NFPA 18A. That standard came about in 2017, but we're currently on the 2022 edition of NFPA 18A. And there's the new testing criteria in NFPA 18A, which we are working on testing to meet that criteria as well. So what is an encapsulator agent? Encapsulator agent is a water additive agent. So we're still using water. We're using lots of it. And we're using either 1% encapsulator agent or 3% encapsulator agent with the water. So it doesn't take very much of the encapsulator agent to make the water much more effective. And the encapsulator agent creates something in the water called spherical micelles. The spherical micelles encapsulate carbon and hydrocarbon molecules, polar and nonpolar solvents, and hydrocarbon liquid and vapor molecules, and it traps those molecules inside of the spherical micelles, making them unavailable to oxidation or combustion. The encapsulator agent separates the fuel from the oxygen at a chemical molecular level.
Encapsulator technology, the next generation of fire and hazard mitigation. First, we start with a simplified version of a single encapsulator agent molecule consisting of a hydrophilic polar head which loves water, dissolves in water, and a hydrophobic nonpolar tail which fears water and will do anything to get away from water. Once the EA molecules enter the water, they instantaneously and automatically orient with the nonpolar tails inward and the polar heads outward, forming millions of spherical micelles. Micelles travel towards and exit the nozzles, forming EA droplets. Micelles nearest to the surface of each droplet automatically break apart. The nonpolar tails orient outside the droplet, with polar heads on the surface, forming an EA skin on the surface of every droplet. In addition to the EA skin, there are millions of molecular spherical micelles within each droplet.
So if we look at that water droplet on the screen, the blue part being the outside surface of the water droplet, because F500 is a surfactant, it allows those water droplets to become much smaller. So if we take a high surface tension plain water and we break it down into much smaller droplets, we gain a lot of surface area. So that increased surface area alone helps it absorb heat more rapidly or effectively than plain water. Another thing is the modification of the structure of the water droplet with the coating of F500 molecules covering the outside and the hydrophilic heads coating the surface while the hydrophobic tails point outward. Creates a very effective thermal circuit to absorb heat into the water droplet and then into the spherical micelles that pack the inside of the water droplet. Inside of the water droplet, those spherical micelles, although it represented on the screen, you probably have 40 or 50 of them in there. In actuality, there's millions and millions of spherical micelles in each tiny water droplet. And each one of those readily absorbs heat as well and helps the water droplet absorb that heat very, very effectively. And then inside of each of those spherical micelles, as the video mentioned, are the trapped carbon and hydrocarbons that would otherwise be the fuel for combustion. So it traps those as it's flying through the air towards the object on fire or the liquid fuel on fire. It traps those out of the vapor space above the fire. And then it also traps those when it strikes the fuel surface and agitates a liquid fuel, for example, and then encapsulates the carbons and hydrocarbons out of the liquid fuel as well. When we're talking about more of a class A material, a solid or a porous material, as it's soaking in, it's not only absorbing that heat very well, it's encapsulating hydrocarbons that would come from the effects of pyrolysis as well. So NFPA 18A section 7.7 specifically of the 2022 standard of NFPA 18A, excuse me, is called the spherical micelle stability test. And it's the test that shows not only that encapsulation is taking place, but it's the test that shows that the spherical micelles are stable in the presence of high heat, and they won't give up the carbons and hydrocarbons after they encapsulate them. So after we go through an encapsulator stability test, we put a torch on the surface of the liquid that we ran the test on, and it does not reignite. Even in the presence of a direct flame contact from a torch. So it not only does it cool and encapsulate, it holds on or locks up those carbons and hydrocarbons and keeps them from being available to combustion for a long time. So the molecule characteristics of an F500 molecule include that polar head and the nonpolar tail. The polar head loves water, and it seeks out water and the surface of water droplets. And then the nonpolar tail fears it, so it hates it, and there's significant distance between the two, enough to make them act differently. It's called an amphipathic molecule. One of the features of that molecule construction is that the F500 in water automatically dilutes itself, so it doesn't settle or layer in the water, and it stays diluted even when it's tank mixed for many, many, many years. So with an F500 solution, either batch mixed or in the hose through an eductor or through what we call a water-driven proportioner, as those molecules are interfacing with water, they flip inward, and then those tails form on the inside of the spherical micelle. And during that process is partially where it does some of the encapsulation. And then as it's striking fuels or passing through buoyant fuels in the vapor space, it traps more as more and more of those spherical micelles are forming. And kinetic energy is an important part of that process. One of the also very important parts of the process or features of F500, I should say, is the molecular weight. The high molecular weight helps it do a couple of things. Number one, It helps it absorb more heat, and it helps it penetrate fuels very effectively. But it also is a feature of something we call the interruption of the coalescence of free radicals, and it eliminates the creation of many of those toxic inflammable compounds that come off of a fire. But a big thing that it does is helps absorb heat into the water droplet. I think there was supposed to be some animation there. There it is. So that rapid heat reduction as the F500 modified water droplet strikes the fuel or interfaces with the surface of the fuel, helps absorb that heat rapidly into the water droplet and into the spherical micelles. And since those droplets are made much smaller than plain water, it just absorbs heat anywhere from 10 to 30 times more effectively than plain water, depending on the fuel. It's creating a thermal circuit, and something we call thermal conveyance into the droplet. We look at a comparison of plain water to F500. Plain water, only 3 to 5% of water actually ends up reducing heat as it passes through the gases and strikes the object. Much of it runs off and doesn't end up absorbing heat, and then the small concentrated amounts that do absorb heat tend to turn to steam. And some of the negative things about steam is that steam comes off at 212 degrees. So if you have victims involved of any sort, you're going to potentially cause them burns, not only to their skin, but to their respiratory tract as well. So compared to F500, plain water is a poor conductor of heat. F500, since it's got a higher boiling point, smaller droplets, packed water droplets with spherical micelles, and the modified water droplet structure, it absorbs heat much more readily. It starts to vaporize at around 158 degrees, and it just absorbs heat more uniformly. So there's no steam that comes off of it. You see some water vapor that comes off of it, and that water vapor is at a very comfortable temperature to walk through or exist in. It's like a warm, comfortable shower. And then even the runoff from F500, it gains in heat as compared to water itself. Water itself gains very little heat as it runs off. So it's been evidenced in the F500 runoff that it has gained a significant amount of heat. So it's absorbing heat the entire time. And then the next, the encapsulation process itself, and the encapsulation of carbons and hydrocarbons as the F500 droplets are traveling through the vapor space. It's absorbing those carbons and hydrocarbons inside of the spherical micelles. And as at least one study that we've received from China, they actually found a way to prove or show that each spherical micelle was gaining weight as it absorbed carbons and hydrocarbons. So we have several features of F500 which help it suppress fire. First is that surface tension reduction. It saturates a wetted surface area, and when it comes to things like combustible dust, which tends to float on the surface of high surface tension water and still combust, it is very well wetted by F500. And it penetrates into tight spaces, pores, and into granular materials like coal, sugar, grains, etc. Rapid heat reduction can take heat in a room from 1200 degrees to 120 degrees in a matter of just a few seconds. Absorbs many more times thousands of calories per hour than plain water. It provides excellent burn back resistance because of the features of both the wetting, the temperature reduction, and the encapsulation of carbons and hydrocarbons. And encapsulation itself forms that chemical cocoon around the liquid and the vapor and renders the materials non-flammable or locked up. And then, as we mentioned, the interruption of the coalescence of free radicals. It helps block those free radicals from coming back together and forming new compounds. So as it's applied, you see that smoke disappear immediately. So if we look at the 3-agent comparison between a wetting agent under NFPA 18, a foam under NFPA 11, or an encapsulator agent under NFPA 18A, we see some differences that helps the encapsulator have a foothold that it's a better agent than the other two typically. Number one, a wetting agent has surface tension reduction, helps it spread and penetrate, and heat reduction because of the smaller water droplets, the more surface area, but it does create more steam than plain water alone. NFPA 11 compatible foams have surface tension reduction that aid in spreading the blanket around fixed objects and sealing on the other side, which is actually a nice benefit. That blanket separates the fuel from the oxygen to smother the fire and keep the vapors from mixing with oxygen in the vapor space. And then heat reduction, the blanket insulates and traps the heat in, which is kind of a negative of foam. It eventually cools, but it's a slow process compared to an encapsulator agent. And then the other thing about a foam is you got to maintain the blanket. So if we're dealing with a polar solvent that's trying to draw water out of your water-laden bubbles, it'll break down the foam blanket. So they put in there something called PFAS, and the PFAS helps maintain that separation. Well, PFAS has a lot of negatives to it, which we've found out over the last 20 or so years. Negative impact on the environment, and it's also a cancer-causing agent. So as they're trying to eliminate PFAS from foam, the foams typically are performing much less efficiently than they used to. So they're trying to overcome that with different chemical makeups of the foam, and some of the chemicals that they're using to do that with are carcinogens as well. So an encapsulator agent has those features which we've already discussed: the surface tension reduction, the encapsulation, the heat reduction, which is very, very quick, much quicker than plain water or foam, and then the interruption of the free radicals. And when you put those all together with the fact that it's applied by very common means and nozzles and no really special equipment, it's a very good agent. So NFPA 18A makes that new third category of agents and makes the encapsulator agent meet that new third category of agents. So it's applicable to Class A fires that are two-dimensional, Class B two-dimensional, and three-dimensional fires, Class K or kitchen fires with grease, Class A, three-dimensional fires like coal, biomass, wood, rubber, tires, because it soaks in very well. Tires are very hard to put out. If you've ever seen a tire fire, they're very difficult to put out because they're dense, they hold a lot of heat, and then with steel belting in tires, they retain a lot of heat. But F500 reduces that heat and puts them out very, very quickly. Transformers, turbines, lube oil fires, things in the power industry, F500 is very effective at extinguishing those as well. Blowing, spraying fuels, F500 puts those out. FDNY and Con Edison worked with Hazard Control Technologies to do some testing, which we'll talk about in a little while. It made F500 applicable to Class C fires, as long as you observe standoff distances and use a broken string. And then combustible metals, magnesium, titanium powder, lithium-ion battery fires, etc. It's it's also applicable to those. Lithium ions, not actually a Class D. Excuse me, the lithium ion batteries are not actually a Class D fire. However, they're really an electrolyte fire in a small canister. And then flammable liquid spill control and vapor control as well. So when we look at power generating facilities and the fire hazards in those facilities, one of the things we focus on and we help our clients with is to detect, correct, and prevent hazards in power generating facilities, and to be proactive about it. Much of that has to take place on the preventive side. But if we can prevent the circumstances that would create a hazard, we can control a lot of that and make corrections in processes and machinery and equipment to where problems could happen. And then obviously early detection is a feature of that as well. So specific power generating facilities hazards involve the bulk storage of different types of fuel, coal, for example, gases, etc. Combustible dust is always a hazard in a coal-fired power plant. Material handling, pressurized oils, specifically in the under turbine lube oil system. Transformers, which are filled with combustible oil and contain high energy. And then energy storage systems contain many hundreds, if not thousands, of lithium ion batteries, and that is becoming a more preeminent problem. So the bulk storage materials, as we look at those, we're looking at mostly at coal and the different kinds of coal. Some of it's more volatile than others and susceptible to either gaining moisture or losing moisture. And either way, with specifically PRB coal as an example, it doesn't matter whether you're gaining moisture or losing moisture. Either way, it's becoming more combustible. So and then coal also gives off dust, and that dust, fugitive dust and float dust, are both hazards. Fugitive dust tends to smolder, float dust tends to explode. So we're going to look at a little video here of a coal fire that occurred in I believe it was in Russia. Where it started out pretty small, but it grew very quickly because of the presence of coal dust on the truss work and I-beams and so forth in the facility. As you can see, the fire is very small at this point. Would have been pretty manageable if they had a system. Doesn't take it very long to start involving that fugitive and float dust that's settling on those beams. And then that dust starts to burn, and then the fire grows fairly rapidly. They also didn't report the fire for 3 hours. They tried to fight it themselves for an extended period of time, and that did not work out well for them. I paused the video for a minute all that smoke that you're seeing, those are the free radicals that we mentioned. And as really right above the fire's surface in the vapor space is where those free radicals are coalescing and coming back together and forming those compounds that you're seeing as smoke. And they are flammable, they are toxic, and with the right oxygen mixture, they will explode, deflagrate, catch fire, advance the fire conditions, etc. So the results, one employee was killed, 9 were injured. A lot of them had carbon monoxide poisoning, which is a big feature of coal fires and coal combustion. 4 out of the 7 units were destroyed, so that makes a big impact on the power grid in that country. So during the initial response, most, I would say all power plants have emergency plans, and when they're not followed, things happen. People get injured, explosions occur, fires get out of control, but also when the plant's not being properly maintained with an eye towards safety, it allows fires like this to occur. So fuels and bulk materials found around a power generating facility include the solid fuels, coals, biomass, petcoke, activated carbon briquettes, refuge gases, and waste. Liquids include fuel oils, lubricating oils, mineral oils in the transformers, diesel fuel, gaseous vapors, include natural gas and propane, hydrogen to keep the turbines cool, carbon monoxide, as well as what occurs in bunkers and silos as coal naturally degrades and starts to combust. And then now, due to the fact that lithium ion batteries are included in battery energy storage systems, that's another type of fuel. And like I said, that's an electrolyte fuel. The nice thing is that F500 encapsulator technology is applicable to all of those fuels. So another feature of energy storage, energy generating plants is storage of materials in piles, barns, and domes. Where I got my introduction to F500 was in a 300-foot diameter coal storage dome. And it wasn't a very fun introduction, as the incident lasted for about 12 days as they let the thing get a little bit out of control, and we had to empty the barn with loaders bucket by bucket. So transfer areas, chutes, bins, hoppers, and silos as the coal is being moved around, or the biomass, or whatever the fuel is. And then from those, you get both fugitive dust that settles and enters up under belts and in void spaces and begins to smolder, or you can have float dust, which is lighter than air, not lighter than air necessarily, but it's easily aerosolized, and it floats and it lands on beams and things that are above your head and shoulders and builds up. And the fact that float dust is so light, any puff of air that aerosolizes it makes it airborne again and very susceptible to becoming an explosion hazard. And then transport around the plant on conveyors, but transport to the plant on ships and barges and rail, and then mobile equipment at the plant as well. So hazard management really requires us to manage that fuel from the time it arrives all the way through handling. We want to be able to make sure that we're preventing fire that's not intentional. We need fire to make the boilers work, right? But we want to prevent unintentional fire. We want make sure we're managing dust appropriately to make sure we don't have a quantity of it that becomes combustible. And then we want to prevent explosion. One of the things we always tell people in training is, once an explosion occurs, it's too late to really do damage control at that point. You have to prevent explosion. You have to keep your facility well maintained to prevent that, because there's no system really to and there's no time really to react to prevent an explosion once one is imminent, or all the factors are there and present for an explosion to occur. Your tennis shoes can't outrun an explosion. So bulk material stockpile hazards include time, wind, sunlight, moisture, the ambient temperature, and then the way the stockpile is managed. Partially and uncompacted bulk material stockpiles can combust when those things aren't managed appropriately. So one of the ways that we manage it appropriately is you compact it to keep the air out of it. Another way is to make sure it's being utilized and you're rotating your inventory and using it up in a timely manner so it doesn't have time to combust. It's a constant monitoring and management process depending on the type of coal your plant is burning. So bins, bunkers, hoppers, and silos. And I know that picture shows a transformer fire, but enclosed spaces, stagnant zones are areas where fugitive dust can accumulate. And in those areas, that fugitive dust can begin to combust spontaneously on its own. And it's susceptible to things like sparks from moving equipment and friction, and belts that get out of alignment, and drag chains that get out of alignment that leave fugitive dust in those stagnant zones. Then the combustible fines, as we said, they tend to float and settle on horizontal surfaces wherever they can find them. Dust traps, inactive silos are another area that, if they're not cleaned out appropriately, you can have spontaneous combustion occur in those. And then if a crust builds up in the coal that's in a silo, you can have a cavity develop or burn out underneath a crust. And then when that crust collapses, it creates a large puff event of dust, and that causes a primary explosion. And then all the float dust that's been left around gets aerosolized and cause a secondary explosion that can be much, much larger. So the impact of the flow of material on fires includes what we call funneling. So the stagnant zones occur as where the arrows are pointing when the material is not moving very well. It gets stuck there. And then if it gets stuck there for too long, it can start undergoing spontaneous combustion. Your carbon monoxide levels can rise. You can have a void space burnout. And some of that has to do with the design of many silos being for one type of coal, and then the coal being switched later on to a different type of coal that's more volatile. If you'll see the angle of the sides at the bottom of the silos, the two on the left, you've got a fairly flat profile that's holding some of that material up in a stagnant zone. Whereas on the right, where it has mass flow, you have steeper sides, which promotes uniform flow all the way through the opening at the bottom of the hopper. So how do you manage that? Occasionally, if you have the low sloping sides, as on the left, you have to empty out one silo at a time, make sure it's clean, then start refilling that silo while you empty the one out next to it. And you have to manage them in that order to keep that from occurring. So prevention includes periodically lower levels or complete emptying of a silo one at a time, so that lower levels, so that that stagnant material does not develop or it's removed. And then you have to verify that that material level is low enough to make sure it's cleaned all the way out. And if you suspect fire, one thing you have to do is make sure you don't add more fuel to the fire or more coal to the bunker, and you're letting it expire, but you also don't want to run coal that is already combusting, and I'll show you why in a little bit. Carbon monoxide monitoring, very critical to being alert to potential fire in your bunkers. And look for indications as well using thermal imaging cameras and periodic walkdowns, smells, and visual inspections. Daily walkdowns are important. So this shows carbon monoxide monitoring as being a great early fire detection method for use in coal bunkers. It's really a necessary method. So as coal begins to combust, it gets up around 200-degree level, and you start to experience a rise in carbon monoxide. And that the carbon monoxide indication is very important. At that point, we want to start monitoring and following our emergency plan. That emergency plan has to exclude opening up a bunch of chutes and doors, however, and introducing a bunch of oxygen. So you want to be able to monitor it externally initially, bringing your team together, following the plan, making sure everyone's on the same plan. The last thing you want to do is introduce unnecessary air or air currents to the system that might be in crisis already. So one of the things that hazard control technology manufactures and supplies is something called a piercing rod kit. It helps you manage your bulk material stockpiles as well as bins, bunkers, and hoppers. So it helps you extinguish deep-seated coal fires following something we call the reverse hazards elimination process. But we can get these piercing rod kits, or we can get these piercing rod kits to you basically up to as long as you can handle in 5-foot sections, and the piercing rod is lowered into the bunker if you're using it on a bunker till it gets to the surface. Then you keep adding rod as you work your way down, and there's a process and some training to go with it. It's manpower intensive, but it does work, along with coordination of thermal imaging cameras and teamwork in a reverse hazards elimination process. One thing we do is we try to make sure that we're eliminating any potential dust or gas explosion in the headspace above the material in the bunker as we're working our way towards the problem, and that we're not going to collapse any kind of a dome or void space in the process. And then in the piles, if they're in a pile outdoors or in a barn, for example, you can use the piercing rod kit to just walk up to those piles more or less and apply F500 into the pile. Dust collection, obviously very important to preventing explosion in a plant. Dust collection, if you look at the dust collectors on the left, those had explosion panels in them, and they did experience an explosion. Those explosion panels are what gives out if an explosion occurs and keeps the explosion from causing mass damage to the system, as well as the explosion going back into the plant. So those panels are a very important safety feature of dust collectors. If they don't have them, the damage could be much, much worse. Dust collectors have a maintenance protocol, of course, and we also have specific training for dust collectors that helps you appropriately manage those, as well as mitigate emergencies that do occur in dust collectors, because occasionally you can have spontaneous combustion within a dust collector, or you can get a hot object that passes into your dust collector from the collection system itself, and then sets the dust collector on fire. And just the presence of all that air and dust, you have an explosive situation, especially with the confinement. These are the explosion panels at work. See how they really reduce and eliminate damage to the dust collector itself by letting that pressure have a place to go besides blowing the dust collector apart. And then on the right, we have a much larger dust collector. And this one has some explosion panels in it. But the explosion panels were welded down. And you can see it blows that dust collector apart, with a lot of force. I accidentally changed slides there and didn't mean to. So you can put an F500 system in your dust collectors so that you can, once you detect a fire, just open a valve, have F500 coat the interior of that dust collector and eliminate the fire potential, cool it off. A couple hours later, you go clean it out, put new bags in it, and you're up and running again. Much less damage is caused by pre-installing a system. So an explosion and or deflagration causes very fast fire travel, and sprinklers don't react fast enough for that to occur, or to prevent that or mitigate that. So we really need to have a system that can detect those problems early and quickly, and a deluge system, because a closed head won't detect fast enough, or won't open up fast enough to control the problem. So you need a deluge system with advanced detection that involves things like infrared black body detection, and so forth. Things that are fast acting and reacting to manage that, along with the prevention program. Combustible dust in solids, particulates, and dust itself. So things like coal dust, sugar dust, grain dust. Those are all combustible dust, and they're referenced in NFPA 652 and 654 as far as codes and management of your facilities to prevent those hazards from occurring. We're going to look here in a video in just a second that shows how, when you aerosolize these dusts in attempting to extinguish them, even, you can cause a bigger problem once you expose them to oxygen, and especially in the use of plain water in an inappropriate stream. So this is at a wood processing facility of some sort. And they have a traditional dust collector, and they have a fire in the dust collector, and the fire stream that's being used is a very narrow stream, maybe even a straight stream, and you'll see why it's inappropriate.
We had a hopper fire today at a wood manufacturing plant.
What crews finally got here?
On arrival, we had fairly heavy smoke coming out of a hopper that had some wood product in it.
And what happened when you guys opened the hopper?
As we were working through the hopper, there was a slight dust explosion that occurred as we were trying to mitigate the fire.
And was everybody okay?
Yeah, everybody is fine.
So what is that dust explosion? Like, what happens?
It's just the dust meets oxygen and catches fire at a rapid pace.
Is it very hot? Is it dangerous?
It can be very dangerous. It has a bit of a concussion feel to it, but it again, in the wrong conditions, it can really hurt somebody.
And once again, everybody was okay.
Everybody's fine, yeah.
And the fire's now under control?
Fire right now, we're still working on it, just making sure it hasn't entered the building.
And how much of a cleanup and overhaul is this going to be?
It should be finally, most of it looks like it's contained to the hopper itself, so shouldn't take long.
As you're seeing them applying the stream, you can imagine with the high surface tension of the water, straight stream, they're really just chasing that dust around, and they're causing it to mix with oxygen. Right? And what's occurring is that the dust is actually sitting on the surface of the high tension water, and it's able to combust anyway, regardless of the presence of water. So with an agent like F500 and the wetting agent, it immediately wets that dust as soon as it interfaces with it, and makes it non-combustible. And then obviously using the right type of stream is important. Although with F500 you can use quite a straight stream for reach and penetration, and not really see that kind of a problem. But plain water definitely not your friend in that situation. So there are 5 elements typically required for a coal dust explosion. So number 1 is your oxygen, fuel, and heat, just like you would have in the fire tetrahedron. But then the confined volume, so some type of confined canister, containment, etc., that holds that pressure in. And then an ignition source, something to trigger it. So that ignition source can come from stagnant material that's in spontaneous combustion, or it can come from a spark from friction, from a chain that's out of alignment, or anything from that regard. But anything to trigger that explosion. And then the more confined it is, the more powerful the explosion will be. You have something that can give, like those blast panels, that can make the power of that explosion much less forceful. So this animation is going to illustrate that you have something typically called a primary explosion, and then that causes dust to be aerosolized or released into the air, and then you have a secondary explosion. The secondary explosion usually causes much more of the damage. And if you can imagine something on a plant-wide basis where there's thousands of cubic feet of available volume and float dust available, that secondary explosion can cause massive damage. So we teach something in our courses, in our coal handling hazard awareness courses. It's called the reverse hazards elimination process. And the reverse hazards mitigation includes stopping all of the operations that help contribute to the combustibles in the affected area, inspecting for and removing combustible dust from the surrounding areas of especially headspace areas at the top of any kind of an operation, in the triple room, cascade rooms, bunker rooms. And we can wash those areas down with an agent like either F500 or our dust wash. And you won't have that floating dust fire. If you use plain water and just start spraying it around indiscriminately, you can actually cause an explosion. So you have to be very careful about how you go about removing that dust, but it does need to be done prior to attacking the acute problem. So we get rid of that secondary explosion capability. And then we apply a coating of F500 to the bulk material surface itself or the acute problem area, as we continue to monitor for carbon monoxide and monitor temperatures with thermal imagers throughout. And it's a teamwork based process. It's critical that it gets done in that order, or you can cause an explosion. Imagine if the explosion you saw a moment ago on the screen at the wood manufacturing facility wasn't internal dust collector internal to their building or facility. The damage caused by that would have been much greater. So common hazards again, pressurized liquids and oils. We'll talk about a little more in detail here. Transformers and really an increased problem with transformers that a lot of people aren't aware of. Lithium-ion batteries and battery energy storage system and others. So under turbine lube oil systems are high pressure lube oil system to keep that turbine cool as it spins. They're susceptible to leaks and failures, and then you've got a big fire problem on your hand, a three-dimensional fire problem. Boiler feed pumps, feeding the boilers themselves, oil ignition systems, so you got oil moving and flames, always a challenge to manage that, and black start generators that start up on their own as needed, can be a fire hazard as well with the fuels involved in those. So again, your under turbine lube oil systems are a three-dimensional Class B fire hazard. And when they do catch on fire, the fire is dramatic and intense. So you have to have a system, typically besides plain water, that can better manage that type of fire. So F500 has been proven to do that, and we'll talk about how that works in just a moment. One thing that you can do is system-wide early detection, and we have a strategic partner called Embedded Logics, and they have something called the condition monitoring platform. They use things like infrared, carbon monoxide, video, and really any kind of detection you want, and connect that into an early notification and decision platform with live video feeds, temperature feeds, carbon monoxide feeds, etc. And it can set thresholds in a server to have certain actions occur, but then also is notifying personnel on their smart devices, and they can look at and monitor real-time temperatures and video of any problem area, and even trigger actions and interventions. So potential fire protection considerations for three-dimensional Class B fires include water. Water is what's traditionally in the sprinkler and fire protection systems for under turbine lube oil systems, but we'll show you in a minute how F500 was able to be more successful in that environment. Foam forms a blanket and traps in heat, but it's not suitable for three-dimensional Class B fires because it's spraying fuels and three-dimensional objects. You can't form a blanket on that. You would have to have a dual agent system. The encapsulator agent encapsulates hydrocarbons and renders them non-flammable and non-ignitable, and it reduces heat much more readily than water and or foam, 6 to 10 times greater versus water. And it's effective on three-dimensional Class B fires. We'll talk about it in a little bit, but FDNY worked with Con Edison and Hazard Control Technologies to do some transformer fire protection, as well as just electrical fire protection up to 345,000 volts at a substation. And F500 was successfully utilized in that situation without return current to the nozzle, as long as the standoff distances were observed and a broken stream was used. So at a Dominion facility, Dominion Power facility, their insurance carrier, FM, was recommending that they up the capabilities of their sprinkler system the application density from 0.20 gallons per minute per square foot up to 0.40 gallons per minute per square foot, which would have cost them millions of dollars. But with full-scale testing, we were able to demonstrate that F500 at 0.20 gallons per minute per square foot reduced the heat faster than the FM Global recommendation. And since it performed so well at 0.20 gallons per minute per square foot, they went ahead and added it to their system, and it saved them. And their existing system was designed at 0.30, so they were very comfortable with adding F500 to their system at that level and not having to upgrade to 0.40. Again, it saved them millions of dollars from upgrading an entire sprinkler system that was already in their facility.
Hazard Control Technologies presents F500 encapsulator technology.
Lights the building. Hey, a little bit longer than a door will fall off. Yeah. We get a good picture there.
Now we're moving into the power transformer segment. Many power transformers are very, very old, and they're very, very hard to come by. Transformers, most of them, or many of them, are made in other countries, not the U.S., and they're not easy to come by. They're custom built for the job. We'll also discuss how they're very susceptible to different kinds of attacks. So large power transformers, did a little white paper on these a while back. The loss of critical large power transformers can disrupt electrical services over large areas of any country. With the U.S.'s security and economy dependent on the reliable delivery of electricity, the impact of extended outages from the loss of one or more large power transformers is a significant concern. And that's from energy.gov. And that can be applied to any country, I'm sure. Attacks and suspicious activity at U.S. power stations reached a decade-long high, with more than 100 reported incidents in the first 8 months of 2022. Since then, there have been at least 18 more publicly reported attacks or potential attacks on substations and power plants in Florida, North Carolina, Oregon, South Carolina, and Washington. And I imagine many of our guests from other countries today have had attacks on their power facilities as well. That makes the U.S. power grid, which spans more than 7,300 power plants and 55,000 substations and 160,000 miles of high voltage power lines, a very soft target. Dr. Granger Morgan of Carnegie Mellon University, who chaired 3 National Academy of Sciences reports on the grid for the federal government, says it is inherently vulnerable because it's constructed in such a way that if one part of it can be destroyed or impaired, it can have a very significant impact on other larger parts of it very quickly, kind of like dominoes. So we did some testing, of course, we mentioned with Dominion, and we got a video here that shows the full-scale testing on extinguishing a transformer fire. And again, transformers carry mineral oil typically as a cooling agent inside of there. But if something like they're shot with a high-powered rifle, for example, the oil can leak out and catch on fire. And this shows how quickly and effectively F500 can put it out.
Hazard Control Technologies presents F500 encapsulator technology.
We're at the Philadelphia Electric Company fire training grounds where F500 is being used to extinguish an electrical transformer fire. F500 is fed at 3% into the sprinkler deluge system utilizing 10 5-gallon per minute heads. The fire is quickly knocked down to include the running surface fire by the indirect spray from the heads.
So with something like mineral oil, it's coming out of there very hot already because it's been doing its job at cooling the transformer. Then it catches on fire, it gets even hotter. So one of the important features of F500 is cooling that oil rapidly, cooling those metal surfaces rapidly to below the ignition temperature of the oil, and as well as encapsulating the oil.
1200 degrees. Fire's out. Fire's out.
So in this comparison, F500 extinguished the fire 3 times faster and at half the sprinkler density of plain water. Another little comparison. So at Duke Energy, they had a fire. They attacked it with plain water. That's the fire on the right. Took 6 hours to extinguish. 2 fire departments, 400 gallons of AFFF foam, 50,000 gallons of water, and the agent alone cost $8,000 to do that. The cleanup costs were probably very significant from cleaning up the AFFF and water contamination as well as with the mineral oil. At Alabama Power, they had a fire with an F500 system pre-installed. It took 3 minutes and 10 seconds to extinguish. No firefighter intervention because they were called off before they ever arrived on the scene. 3 gallons of F500, 100 gallons of overall solution. The agent cost $100 and no cleanup costs. So that's a big difference when it comes to cost effectiveness and the potential for damage and cleanup costs reduced. So there are a lot of different ways to bring down the grid. Cyber attack, physical attacks such as gunshots. And again, there were a lot of gunshots in the past couple of years. High-powered rifles shooting transformers from a distance. You can have a lone gunman doing that. Just someone who's a little bit mentally handicapped maybe, or has an agenda. But you could also easily have a group that organizes or coordinates to do that on purpose. Electromagnetic pulse. We tend to focus in our industry on accidental causes, but there are intentional causes as well. And the world's always got some type of unrest going on. But electromagnetic pulse can come from nuclear weapons, theater nuclear weapons, and nuclear weapons that are specifically designed just to create an electromagnetic pulse and knock out large areas of the grid. Natural disasters, extreme weather and lightning, and supply chain issues as well. The results of those things include oil leaks, overheated transformers, threatening to ignite, fires, grid failure, and power failures. According to Grid Security Now, which is a grid security watchdog, roughly 38% of electric disturbance events in the US are due to physical attacks, which was really surprising to me. 2% are due to cyber attacks, and 53% are due to weather events. So this is a substation not too far from where I live. It's in Grand Island, Nebraska. And it's a pretty large substation, and they've started to build commercial and residential areas around it. So I think partially for aesthetic purposes, but also to help protect it from things like high-powered rifle shots, they built a concrete paneled wall around that substation. From street level in a vehicle, it's very unnoticeable, which is part of probably the feature of it. You know, if you cover up your valuables in your car, you're much less susceptible to getting them stolen just because they're out of sight, out of mind. And that's probably part of this feature. But those are the concrete panels that slide in between the concrete posts, and they make an effective barrier to gunshots and things of that nature. And then they also make it much more aesthetically pleasing. Just a physical protection instead of just a fire protection. So let's talk a little bit about F500, what we call concentrate control supply systems, or our proportioning systems that help proportion F500 into sprinkler systems. They are very applicable to transformers, turbines, critical coal handling system components, and we've designed and supplied components for each, as well as we do on-site commissioning and startup for those. We have direct application on transformer fires at 3% because it is a petrochemical fire with the oil involved. If you're doing manual firefighting, as long as you maintain that appropriate standoff distance and use a broken stream nozzle, you don't have that current flow back to the nozzle. And if you're using FM nozzles, an FM nozzle is a nozzle, a fog nozzle, all brass, that won't go to a straight stream. It's always a broken stream. And then we have mobile and portable delivery systems as well. We have portable water-driven proportioners and encapsulator agent trailers. So you can attack a transformer fire, for example, anywhere on your site or at substation sites as well. This is a diamond doser, water-driven proportioner, typical installation. As you can see, the concentrate tanks over on the right, they're just totes on a leak catchment basin. It's just fed into the water-driven proportioner. As water travels through the riser, it proportions agent into the riser at the appropriate percentage as it's set. And then when you use advanced detection systems like those by Embedded Logics that we partner with, it helps cool any kind of fire really, but three-dimensional fires, liquid ignitable fires, fires discovered in conveyor belts and so forth very, very quickly, and transformer fires. So HCT works with sprinkler designers, installers, and contractors to supply systems, proportioners, and agents specifically engineered to our clients' needs. We provide engineered solutions, on-site commissioning and startup. And we've done that for many, many years for many clients all around the world. So some rapidly developing hazards that everyone should be aware of and how they need to be approached includes the two-dimensional and three-dimensional pressurized oil hazards, energy storage systems, lithium-ion batteries, and combustible metals. So this is a typical battery energy storage system associated with the solar field. So as the sun heats up and starts the energy flowing from the solar field, that energy is stored in the battery energy storage system for use on the grid as needed. But each one of those containers contains racks of hundreds and thousands of lithium-ion batteries. And 2019 in Micken Battery Energy Storage System in Surprise, Arizona, there was an explosion that injured 4 firefighters at a battery energy storage facility. There was a fire, and the fire department got there. They waited for a couple of hours before they approached and opened the container up. Once they did open the door to the container, they had an explosion. It blew 1 firefighter through the fence and another one over the top of the fence and injured 2 others. This energy storage system was placed into service in 2017, which is prior to the publication of NFPA 1855, which probably wouldn't have made a difference anyway, because 855 doesn't really address suppression systems. It addresses the fire resilience of the structure. The system was comprised of 10,584 LN lithium, nickel, manganese, cobalt, which is abbreviated as NMC, battery cells organized in modules and racks inside that specific walk-in enclosure. So one of the big hazards behind that is that you have a container in which batteries start to off gas, and then you can have a partial or full volume deflagration. So here in the video we're going to show you, we show how F500 successfully extinguishes a lithium-ion battery module on fire, like what might be in a single rack in one of these enclosures. And we are currently developing systems with best designers and so forth to develop in-rack systems as well as container systems that will successfully mitigate these problems. I'll try and advance this for you. So this was an experiment done at a university in Germany. And you're going to see that the thermocouples over here on the right start to rise in temperature. Watch number 5. It starts to rise in temperature and gets up around the 500 or 600 degrees Celsius mark. The system is activated. The F500 at 3% goes on to the batteries. The batteries quickly go out as the encapsulator agent encapsulates and cools the electrolytes coming out of those batteries. As you'll notice, the fire kind of comes and goes as the different cells go into thermal runaway and start to spew the electrolyte out the ends. It's really an electrolyte fire, and you've got just these tiny little canisters that can't contain that heat in the electrolyte. And so you have these small jettisoning flames and explosions that occur. Very characteristic of a lithium-ion battery fire. Plain water doesn't soak in between those cells or into the cellular layers very well because of the high surface tension, but F500 does. Encapsulates the electrolyte, cools the batteries off quickly, and they're permanently out in a matter of seconds. And the temperature's back down to ambient temperatures. But everybody has to be aware of battery energy storage systems. As batteries in a lower state of charge, they tend to emit more explosive, flammable, and toxic gases and fill that container up. Any ignition source, either internal or external, can set it off into an explosion. So an F500 system built into a battery energy storage system is an excellent solution to prevent that in a non-human intervention way. All right, went one too many slides. We're almost done, I promise. So some of the services that Hazard Control Technologies offers specifically within the power industry, consulting and training, is a coal handling fire protection assessment, dust hazards analysis, emergency preparedness and response planning and training, on-site subject matter advisory for heat events, fire events, etc., and post-incident root cause analysis. And then we have training courses such as combustible dust hazard awareness, bulk storage hazard awareness, coal handling hazard awareness, and emergency response training. we show people how to use our piercing rod systems and do the reverse hazard elimination process, better maintain their facilities, etc. And those training courses are available to anyone. Well, thank you everybody for participating and getting up in the middle of the night where you're at to listen, and I sure do appreciate your participation and looking at your hazards and ways to prevent them and ways to deal with them.